All right, I guess we're as good to go as we will be. So let's start. Thank you for your patience watching us follow through this. Welcome to the second day of ESET, of the first East Asian School on Information Theory. You guys are making history here, as our speaker. So today, Professor Alon Olitsky will be talking about his fascinating recent work on learning from big data and information theoretic perspective. Let's see how long the big data theme lasts throughout any big data coming up, Ruby? So if we're talking about some recent work we've been doing over the last few years, it's won a significant amount of attention, including a Best Paper Award in information theory transactions. Um, Professor Ron Olitsky, again, in the interest of not embarrassing everyone, including him, he's known for a variety of things. He's done many interesting things. He's currently faculty at the University of California, San Diego. I think I'll leave it at that. And also, of course, he's the organizer of the Information Theory Application Coursework for every year for the last 6 years. I'll leave it at that. Let me quickly also mention, since some of you said you would like to see the slides, we have posted the current version of the slides on Piazza. So you should be able to see the current version of the slides. But since this is sort of a learning talk, so Professor Olitsky will change the slides throughout the talk. Like I think you post an updated version of the slides after the break is what he promised. So keep looking at the slides as they change.
I had Rudiger work on them. So.
Is there anything else you'd like to
No, thanks.
any other announcements? All right. The rest is pretty much the same. We'll have the talk in the afternoon and lunch from that.
Okay, very good. Okay, so thank you very much, Sid, for the introduction. Thank you, the organizers for inviting me, and thank you guys for coming. So I'm going to talk about learning for big data with an information theory perspective, and this is joint work with 3 of my students, Jayadev Acharya, Ashkan Jafarpur, and Ananda Tirtha Suresh. And as you'll see in the talk, green means good. And so that's how the color was chosen. And I highlighted Ananda a little bit because actually the work that I'll describe today is mostly he has done stuff that he has done. Jayadev and Ashkan have done some of the work here, and they've done some other work that I will not talk about. Okay, so first an overview. So as Sid has said, we have been working on various aspects of information processing, and that include modeling, which is finding a probability distribution that generates a given data, compression, succinctly representing data, prediction, trying to guess what the next value in a stream of data is going to be, learning, which is things like classification, clustering, and extraction of information from data. And the challenges in these problems are several, and they include large domains. So you're trying to learn the distribution of a large domain, so you have many parameters to learn. Sometimes they're even non-parametric, so it becomes computationally even more difficult. Some problems have high dimensions, so the structure will be complex, and some distributions are continuous, and we typically try to make minimal smoothness assumptions, that makes it more difficult. And in all these works, or most of them, we've been taking an information theoretic approach, and that means that we're concerned about efficiency. We want to make optimal use of the data that we have. Universality, we want the technique to work for not just for a single problem, but for a large class of problems. Competitiveness, we want what we do to be as well as what anyone else could do. And the tools that we use are also information theoretic, including Jensen's inequality, Fano's inequality, and others. Okay, and hopefully, when you listen to the talk today, you'll see that if you combine information theory and learning, you get something that is very basic, clean, and I would say somewhat surprisingly unknown. Some of these things are fairly simple. You'd think they would have been known. And today I'm going to talk about 2 topics. The first one concerns large discrete distributions and going to subtitle the art of the doable, because we're going to look at what can be done and what cannot be done. And the second part is about continuous distributions, and I subtitled like that, although just judging from the speed that we've been going, I don't know if we'll get too much of that. Okay, so the first part is learning large discrete distributions and the art of the doable. Okay, so introduction. We are going to look at problems of learning discrete distributions over large domains, and we'll look at 3 problems. The first one is distribution estimation, where we'll be trying to minimize the number of samples that we need to learn the distribution. The second one is compression. We'll try to minimize the rate, the number of bits we use to represent the data, or equivalently, we try to optimize the prediction with log loss, predicting subsequent values. And the third problem is classification. We will try to minimize the error, classification error. For each of those problems, we're going to show that in some sense this problem is impossible. You cannot do it optimally. And then we look at a natural modification, or what we believe is a natural modification. It will be up to you to see if you agree. And then we show that with this modification, it turns the impossible into possible. Okay, and once
we agree that it could is invisible.
Oh, okay. Okay. Being green here, so using a little light. Okay, so it's kind of going to be a little problem because all the good things are going to disappear. Okay, so. All right, so once we get something possible, then we try to find optimal or near optimal solution. And of course, the benefits of making something possible are several. One of them is that it provides encouragement. Like if you say something is impossible, maybe you'll just give up and not do it. If you say something is possible, then at least you have hope of being able to do it. Another advantage is you can evaluate. Once you get something that is possible, you can see how close you get to the best that you can do, as opposed to impossible, which is always bad. And then once you say something is possible, you can write algorithm, build circuits that implement them, and then you can apply it to different things, including applying it to the original task, which was impossible, seeing how the possible solution applied to the impossible one. And of course, something that we care about a lot is it allows you to understand the problem. Okay, and we're going to concentrate on examples and results. Okay, all right. And so as Professor Tse has said, in this talk, green means good, red means bad, and blue means, I don't know, but still pay attention. Okay, all right. Okay, so we'll start with the first problem of distribution estimation. And we'll start with, what probably may have been the original sin. So everyone has their own opinion about what has been the original sin. With the agreement? Okay, so, like I'm sure Professor Urbanke has his opinion. Some other people may think that this may have to do with the original sin. Okay, but I think that probably the original sin has to do with probability original sin. So this is the original sin of probability. Here are Adam and Eve in the Garden of Eden, and they're gambling, they're flipping coins. Okay, and of course, after a very short while, they'll try to estimate, get smart and estimate the bias of the coin that they're flipping. Okay? So you have a coin, has probability of heads, probability of tails, they sum to 1. And you want to estimate, or they want to estimate the probability of heads. And so they flip the coin n times, and we let nh be the number of heads. And then the most basic estimator is the empirical frequency estimator. I denoted here by f for frequency, which is just the number of heads divided by the number of coin flips. Okay. And so, for example, if you flip the coin 5 times and you got 3 heads, then the empirical frequency will say the probability of heads is 3/5. And this estimator works because by the law of large numbers, what will this estimate, of course, is a random number, but it will converge to what? It will converge to the right probability of heads. And why is that so? Because for any number of flips, even one flip, the expected value of this random variable is what? pH. So it has the right expected value. Okay. And so the expected value is correct, and the standard deviation shrinks, right? The standard deviation of this estimate, this estimator, you just look at the number of heads, which is binomial distributed, and you normalize it by n. So it's going to be the standard deviation of the binomial distribution, n times pH/pt, and normalized by n. So it's going to be go down with n. Okay, so we have something with the right expected value, the standard deviation shrinks, you'll get to the right value. Okay. So it's almost always at most 1 over square root of n. Okay. So if you want to estimate, the probability of heads to within some value delta that someone gives you, say 1%, and you want to do it with high probability, then what you want to make sure is that delta is less. You look at the standard deviation and make sure that delta is bigger than some constant number of standard deviations. Okay. So we know that the standard deviation is less than 1 over 2 square root of n. You want some constant, so if you ensure the delta is bigger than c times this number, it's also bigger than c times c standard deviations. So you want to make sure that this holds, and therefore n, move n to the other side, and you'll get n is c over 4 delta square. And we're not going to care about the constant, so n is going to be proportional to 1 over delta square. Okay. So we see that as delta goes down, the number of samples you'll need will go up, like the square of 1 over delta. Okay. And this number 1 over delta square will appear also in subsequent slides. Okay, so okay, so this when you do this, there's some probability that you'll be wrong. Clearly, like you could get maybe all of them could be heads, or all of them could be tails. There could be there's some probability that could be wrong. And if you want to ensure that the error probability is less than some epsilon, this gives you some constant, because you looked at some constant of standard deviation. There's some probability that you'll be away from that. If you want to ensure that your error probability is less than epsilon, then you need the same number and you multiply by log of 1 over epsilon. And if you want like a problem for students to think of, maybe this could be one. Okay. All right. Is that okay? So what we see here is that the dependence on epsilon on the error probability is very small. It's just logarithmic. Grows very small as opposed to 1 over delta square. So in everything we're going to talk about, we're going to assume that epsilon is 1%. So you allow yourself 1% error probability, otherwise multiply by some small number. Okay. All right. Okay. So the number of sample complexity we therefore say is S, the number of samples you need for delta accuracy, is 1 over delta square. Is okay? All right. So this was an example of flipping coins, right? So when you flip coins, your alphabet size is 2, okay? And what is that useful for? It's useful for homework. It's useful for the first example in a talk. It's useful for maybe information theory. But for most applications, even gambling applications, most of them, the alphabet is bigger than 2. Okay, so the alphabet is much larger. Okay, so of course, if you're in Hong Kong or in China or Taiwan or Singapore, your alphabet is already several thousand characters. Okay, but if you do genetics, like Professor Tse, he was telling us his alphabet was, well, if he's looking at genes, it's going to be larger. So, or if you do population estimation or genetic analysis, then the alphabet is number of genes, which is 25,000. Okay, if you do language processing, like speech recognition, machine translation, and so on, then, for example, you may want to do text classification. Document comes in, you want to classify the topic, and so on. Then your alphabet is the set of words, which in English is 500,000. Okay, and if you do marketing, so let's say you are Netflix, you want to send people movies that they're going to like, or you're Amazon and you want to advertise proposed products that people are going to buy, or you work for Facebook, then your alphabet size is movies will be maybe many thousands, Amazon will be many million products, and Facebook or WhatsApp, it will be $16 billion. So your alphabet is actually fairly large, yes?
This is exercise number 4, and this is like the learning technology beats the Elmers.
Mm-hmm.
That problem has an alphabet size of 4 to the power of L.
Mm-hmm.
So if L is 100, the alphabet size is 4.
Okay, perfect, thanks. Okay, thank you. Right, okay. So, good. So now maybe people have a reason to stay. Okay, thanks, David. All right. So, in general, when you look at big data like genomics, your alphabet size is often fairly large. Okay. So, so what we want to do is we want to look at the sample complexity for large alphabet. We looked at we found the sample complexity for alphabet, or smallest alphabet, interesting alphabet size 2. We want to look at the sample complexity for large alphabet. So instead of alphabet of size 2, we're going to call the alphabet size now K. Okay, and I'll ask you to remember that K is the alphabet size. The reason I'm asking you to remember is because I gave a similar talk some time ago, and then someone came to me after the talk and said, "Oh, I really liked the talk, but I had one question," and the question was, "What was K?" So try to memorize at least that much. Okay, so okay, yeah, but okay, so so a distribution is going to be P1 up to Pk. These are the things we're trying to estimate, and they belong to the simplex. And we're getting n samples distributed independently according to P. And from that, we're trying to estimate E1 is the estimate for P1, and so on up to Ek, the estimate of Pk. And this estimate is based on the sample that we got. Okay. So we're looking at the number of samples that we need to approximate P, any P in this simplex, any distribution of K values to distance delta. And if you have an estimator E, this is your estimator, then the number of samples that it needs will denote by SKE. Okay, it's the minimum of a number of samples that you need, such that for every distribution, every possible K element distribution, the probability that the distance between the actual P and your estimate is going to be less than delta with probability bigger than 99%, because remember, we're allowing ourselves 1% error. Okay, so is that clear? Yep.
P, you mean the sum?
No, you're trying to, okay, so.
No, but you mean the sum of the differences between the L1.
So yeah, so that's going to be the next line. Okay, and then maybe next line after this. Okay, and then so this is your estimate for a specific estimator E, and of course we're interested in the best estimator, so we're going to look at the minimum of all estimators of the number of samples that you need to estimate the distribution to within distant delta. Okay, so this is Sk of delta, is the number of samples if you use the optimal estimator. Okay, and now Professor Urbancase asked what is D, and so and why do we care about this? Why do we care about sample complexity? Because we think, and I think this is maybe a little bit information theoretic, we think we care not just about computation, but we care about samples. We care about how many, the length n of the sample that you get, because we think samples are very important, because every sample could be a document, like you're trying to classify, every sample will be a document, or so you're trying to learn the distribution of documents in a particular topic. So every sample is one document from there. Or every sample is a person's genome. We try to find like a correlation between the disease and some genes. So every sample is a genome of a person. So even though, as David told us yesterday, the price has gone up, but still it's $1,000 per sample, and you need to find these people. In the patient. So these samples are very hard to come by. So you need to try to minimize this sample complexity as much as possible. Okay. So so the question is, so I'm sorry, what I said was one line is many lines, but okay. So what we wonder is, what is the dependence on delta? So as delta becomes small, how many more samples do you need? But in this talk, even more importantly, we care about the dependence on K. As the alphabet size increases, how does your sample complexity increase? Okay, so that's what we'll mostly talk about. How does the sample size depend on K? And so finally, what is D? So we'll concentrate on two relevant distance measures: the L1 distance between the distribution and your estimate, between P and your estimate. And we care about L1 distance because it's useful for classification and machine learning. That's the distance that comes into play. And it's defined the distance between P, the actual distribution, and E is summation of the actual probability minus your estimate, absolute value. And the second distance that we'll care about will be, in information theory, will be, right, the KL divergence, which is useful if you try to compress data or predict data with log loss the same. So we'll care about these two distributions.
What about L infinity?
We,
Because of that.
so if you have a bound on this, first of all, we'll give you an upper bound on the L infinity norm, which is just the maximum. But also we care a little less about that because we've looked at this now for a number of years and we've seen what other people do. If you try to apply it, typically these are the things people use. If you're trying to do compression, you care about KL divergence to look at redundancy, that's what you care about. If you try to do problems like classification, clustering, it's L1. So we firmly believe these are like two of the main distances to look at. And actually, I'm not trying to overload you, so I don't even, I could have done just one because I just want to show how the difference on K. But if someone wants, they can, could look at the other distances as well. All right. Okay. So, so that's what we care about. How does the sample complexity increase with K? So first, let's show a low bound on the sample complexity as a function of K. So what I want to show you is that if you're trying to do L1 distances, again, you could do it for KL divergence, but I'm not trying to show you all options, so I'll just show you L1. Then what we're going to show is that if you're trying to estimate your distribution to within L1 distance of 2/3, which is very, very weak, normally maybe you try to estimate to 1% or 10%. But even if you just want to do 2/3, you're very crude in your estimate, you still need at least K/4. You still need a linear number in the alphabet size. So let's show that. So it's clear what we want to show. If you want to estimate a distribution over K symbols, you want to estimate it to within L1 distance of 2/3, which is pretty weak, not 1%, just 2/3. Even then, you need the linear number of samples. Okay, so what we're going to do, in order to do it, what we need to do is we need to find a collection of distributions and show that no matter which estimator you'll come up with, at least one of those distributions will require K/4, should be K/4 samples to get this distance. Okay? Right. So what we're going to do is we're going to look at uniform distributions over arbitrary K/2 element subset of 1 up to K. So alphabet size has K elements, right? So alphabet size is 1 up to K. And we're going to look at all possible uniform distributions of size K/2. Okay? If I tell you, if I fix one distribution, clearly I can just do the estimator, estimate that distribution. I don't need any samples. So in order to prove a low bound, I need to look at a collection of distributions and show the estimator will be bad on at least one of them, right? Because we're looking for estimators that are good for all distributions in the class. Okay, so we're looking at the collection of all uniform distributions over half the elements from 1 up to K. So here, we're going to let K equals 20. So this is our alphabet. And our distribution will be on half the alphabet. So our distribution will be on size 10. So here we have a distribution which gives positive probability, uniform probabilities to 10 elements and 0 probability to the remaining 10 elements. And so each one is probability 1 over 10. So this is the actual distribution. And now, what we say, suppose we want to show that you need at least K/4 samples. So it says, suppose you pick less than K/4 samples, okay? And we want to show that in that case, you'll make a mistake. Your L1 distance will be large, okay? So if you take less than, so intuitively, this is very clear, right? Because you have a uniform distribution over K/2 samples. You take K/4 samples, you'll be able to find maybe K/4. Half of the elements you'll be able to find, the rest you'll have to guess. And since you're guessing, you'll make some constant error. So intuitively, it's very, very clear. Everyone agrees? So you have alphabet of size K, you have a uniform distribution over K/2, but we're only allowing ourselves K/4 samples. So you'll see half of those K/2 elements. Those elements you'll be able to know, but the rest you'll have to guess. And you'll make a constant error, and this constant error happens to be 2/3. Okay, so let's just see that. So if we're taking K/4 samples, so we'll observe at most K/4 values. In this case, we'll observe at most 5 values. Okay, so for those 5 values, the best thing you can do is you can, for those that you observed, you can give the actual probability because you know that the probabilities are 1 over 10. So we give them probability 1 over 10, okay, which is shown here. So we give them probability 1 over 10. But for the remaining elements that you have not seen, you need to guess. So for the 3/4 K elements that you have not seen, you better give uniform distribution, and then so you give half the probability to those that you have seen, and you take half divided by 3K/4, so you get 2 over 3k, that's the probability to give to everything else. Okay, so these are the probabilities you give to things that you have not seen. Okay, and then when you look at the L1 distance between them, it's not so important to get exactly 2/3, but you can just do the calculation and you'll get 2/3. Is that clear? And it's clear why, right? Because on a constant fraction, you're completely off. So is that clear? Okay, so I'm describing to you a collection of this. I want to show you that the sample, so that if you want to estimate the distribution over k elements to L1 distance of 2/3, I want to show you that you need at least k over 4 samples. If you have an estimator that works for every distribution, you will need at least k over 4 samples. The way I'm doing it is I'm giving you a collection of distributions, which is a subset of all distributions, and it's a simple subset, so I can calculate like here. And I'll show that even for this subset, if you take any estimator, there'll be one distribution for which it will make. So the collection of distributions, collection of uniform distributions whose support size is k over 2. So our k was 20, so our distribution now is going to be over 10, so each element is probability 1 over 10. So does that answer your question? And once you observe a value, like here, once you observe a value, you better give it probability 1 over 10 because you know the probability, you know it has positive probability, and you know it's 1 over 10. So that's a problem. Yeah, because we said we're looking at distribution, k is fixed, so everyone knows k. We're designing the estimator, we know k. Is that okay? Are we okay? Yeah, that's right. You need to do a little bit of math to show this is the best, but it is. Okay, good. Yes?
So is the intuition that you have k different possible values and linear k observation and see some
correct, some constant function. Yeah, that's right. So if you have, so it's exactly correct. You have k over 2 values, proportional k over 2 in this case, and each of them is equally important because it's uniform. So you need to see, to estimate it, you need to see almost all of them. If you take a constant fraction, you'll be off by a constant. That's what this shows. Okay, so hopefully everyone agrees that the sample complexity grows linearly with the alphabet size. If you want to estimate to L1 distance, which is constant. Okay. Okay. So I want to move from Sk, which is the number of samples you need for alphabet of size k, to S infinity, the number of samples that you need when the alphabet is large, maybe infinite or maybe you don't know. So so for L1 distance, we showed. Actually, you can show that I'm sorry. So we showed that you need at least something that goes proportional to k. Okay, and the question is, how does it behave with k and delta? In fact, you can show that it behaves like k over delta square, and and you can get it by using empirical frequency and standard deviation arguments, like we did in the first slide. So in the first slide, we show how do you estimate distribution over 2 elements. You can get this here too. Intuitively, it's also clear because we saw that to estimate one value, you need 1 over delta square samples. And here you try to estimate k values. So you need to see each one of them 1 over delta square, and you multiply by k because you want to estimate all of them. So intuitively, I think this should be fairly clear. Okay. All right. So what is the problem with that? So is that okay? Who is with us? Who understands what we have been? Or one person? No, good. Sorry. Yeah. Okay. So to see why this is bad, suppose that you're looking at alphabet of size, like English words, 500,000, and you want to estimate to 1%. Then you need k over delta square, which is 5 billion. You need 5 billion documents to do it. That's a large number. Okay. Okay. So if you do KL divergence, the results will be somewhat similar. So instead of k over delta square, you'll need k over delta, but again, it goes linearly with k. Okay. And the question is, what if you don't know the alphabet size and you want to guarantee? You want to say, okay, I can estimate the distribution to within a certain distance. So in that case, you need to worry about the worst k. So if you say you want to, you're asking how many samples do you need to estimate the distribution to within delta, let's say 0.5, and you want to guarantee it, but you don't know k. Okay, then the only possible guarantee you can give is you take the maximum of all k, and that will be what? the maximum of all k of k over delta or k over delta square will be infinity. Thank you. Okay, so that means that if you don't know the alphabet size and you want to make sure that you can estimate 0.5, you need to take infinitely many samples. There's no fixed number. Even a trillion samples do not guarantee that you can estimate 0.5. Okay. So this is what I just said. If you're asking, so there's no number of samples that can ensure that you can estimate the distribution to within L1 distance 1/2. Okay. All right. So so this is where we stand. So we said that the number of samples grows linearly with the alphabet size. If you don't have a bound on the alphabet size, you need infinite. Okay. So since we're talking about the art of the durable, we should talk about prior art. So what have people done? So in order to avoid this concerns, what some people have done is they've looked at some assumptions on P. For example, assuming that P is monotone, decreases, or a model goes up and down. So there are several people looked at it. And in that case, they could show that the number of samples you need goes not linear in K, but polylogarithmic in K. Okay, so if the distribution is monotone, then you don't need linear, you need polylogarithmic in K. Of course, one concern there is who says that the distribution is monotone. I have a distribution of probabilities of words is not monotone. Our words start with E that are more likely that words start with A. Other assumptions people have made is they don't allow all possible probabilities. So, so the Valiants have looked at saying that each probability is bounded below by something. So all probabilities are either 0 or bigger than 1/k. Okay, and then they can estimate the support size and the entropy using k over log k samples. So it's not linear, but it's almost linear, k over log k. So it's a factor of log k improvement. Okay. They have an upper bound on k. Yeah, correct. Right. So most of the things are 0, maybe, and then everything else is at least 1/k. So I mean, so all the probabilities 1/k, the rest should be 0. Okay, and okay, so what are we doing out of the durable? So so we want to look at completely general distributions. We don't want to make any assumptions. Okay, and we want to estimate not the support size or the entropy. We want to estimate the actual distribution. Okay. And the question is whether we can make a small change to the problem. We know if we don't change, we have a theorem, right? I mean, we showed the example that you need k over 4. We saw that. But can we make a small change that will make it durable from something that requires infinitely many samples to something or linear in k to something that will grow slower? Okay. So we're going to make this. Well, hopefully you'll agree it's a natural modification, and which you can call it total probability estimator. And we'll hope that Sk, the number you need for k samples, will reduce from k. So what would you hope it will go down to from linear in k to what? What would you hope for? Okay, so log k would be a huge reduction, right? Maybe you'd hope that from k to go to square root of k. That's a pretty strong reduction. Log k would be a really strong reduction, correct? Correct, maybe correct, yeah, correct. And log k would be extremely good, right? But in fact, we're trying to get it down to a constant. Okay? So we're trying to get infinity down to a constant. Okay, so we want something that no matter what the alphabet size is, we can guarantee with a constant number of samples you can do it. Okay, so obviously we need to change the question, and that's what we'll have this modification that maybe you'll agree is natural. Okay? Right. So what is total probability estimation? So let's look at any natural estimator that you can come up with. Any natural estimator will assign the same probability to all symbols that appear the same number of times. For example, suppose you have a distribution over A up to F, okay? And let's say you took 5 samples and you see CA, CDA. Okay, this is the sample that you saw, okay? Then any natural estimator that will come, so A and C appeared twice, so any natural estimator will give the same probability same estimated probability to A and C, right? Because both of them appeared twice. It makes no sense to give them different probabilities. B, E, and F did not appear, right? And there's no B, no E, no F. So any estimator should give them the same probability. It makes no sense to give B more higher probability than A or F, because they've seen them the same number of times. So what is the motivation? So all natural estimators behave this way, right? Anything you come up with, if you wanted to do something else, how would you decide even how to break the symmetry? Not clear. Okay. And I know David looks very suspicious, so there's no catch. So, what's that? Yeah, like yesterday, like on the street, and you think that it's the same. No. Okay. So any other estimate that someone would give you, any estimate that does not obey this is what we have to say about it. Okay. Okay. And you can also rigorously justifiable if you come up with any kind of like an estimate for the quality. If you do something, then it will work better for something and works for something, and by convexity of all these measures, it will do worse because on average, you're doing worse. Okay. So, this is what we think. And therefore, a natural modification. So this so far there's no doubt, right? So, but the natural modification that therefore we're looking at is we're going to look at estimators that assign the same probability to all symbols that they give the same number of times. So we're looking at these kinds of estimators. And equivalently, if you do that, then we can just look at the total probability of all symbols that appear any given number of times. Okay, because I think I said, because, and we'll evaluate this total probability. So, okay, so we're looking at estimators that assign the same probability to all things that appear given number of times. So without loss of generality, look at all things that appeared 3 times, and just look 3 times the probability give each. That's one-to-one correspondence. Okay, so we can just look at that. Okay, and we evaluate this total probability. Okay, so more precisely, T, the capital T stands for total probability. So TT is the sum of all probabilities of symbols that appear T times. Okay? So in our example, this example, and A, D, C, D, then A and C appeared once. Therefore, T1 is PA plus PC. D appeared twice. So therefore, T2, the total probability of things appear twice, is just the probability of D. And BEF did not appear, so therefore T0, the total probability of things that appeared 0 times is PB plus EPE plus PF. Okay? Okay, so a couple of small remarks. So TT depends on the data. So this number is not something that you can look at the distribution and define ahead of time. I give you, so the distribution is something, right? It's PA, PB, PC, PD. Let's say I give you those values. You cannot tell me what T0 is, what T1, because that will depend on the data. Okay, but it's okay. It's data that you observe. Okay, so it's okay because you'll see the data and just say, okay, these things I've seen them appear 2 times. So here's the total probability to give them. That's fine. Just do it in retrospect. In some sense, one could say that the probability of individual things, if you try to estimate P and PC, is impossible to estimate because you lost that information. You think they appear the same number of times. You cannot separate them anymore. And another comment is that T0 is what people call the unseen or missing mass, right? It's the total probability of things that you have never seen. Right. So, ET is going to be our estimate. So our estimate ET is the estimate of this total probability of the things that appear T times. Okay, and if you wanted, so this is our estimate. We're just trying to estimate the probability of all things that appear T times. And if you wanted to estimate the probability of individual symbols that appear T times, then you just divide, right? So let NT, the number of symbols that appear T times. And for example, N1, how many symbols appeared once? There are 2 symbols, right? A and C appeared once, so N1 is 2. And N2, how many things appeared twice? 1 is just D. And N0, there are 3 things that appeared 3 times. And then you just divide, so the probability that you give something that appeared T times is going to be the total probability divided by the number of elements that appeared that many times. So for example, A and C appeared once, okay? So EA, the probability that you give them, is just E1, the total probability you give things that appear once, divided by N1, which is E1 over 2. Clear? So there's a one-to-one correspondence. Okay, so any questions so far? Right. So, what, again, we need to define our measures of optimality. So the actual distribution now is going to be T0 up to Tn, the total probability of things appearing 0 times, once, and so on up to n times. And our estimate is going to be E0 up to En. And then we can again look at the same distances. We can look at the L1 distance, which is the summation of the absolute value of the differences, or the KL divergence. Okay? And again, we look S, the S is going to be the sample complexity, the number of samples that you need, but now you're not trying to estimate the individual probabilities, you're trying to estimate the combined probabilities, and we call it by tilde. Okay, so this is for specific estimator E. It's the number of samples that this estimator needs to estimate the total probability to within distance delta, and then S tilde K is the number of samples that's required by the best estimator. Okay, and then S infinity, just like before, is the maximum over K. Like if you have no bound on K, just take it to infinity. And we know that S, that for L1 distance, you needed, if you want to estimate the actual probabilities, you needed K over delta square. And therefore, the worst, for when there's no bound on the alphabet, you needed infinity. And the question is, how many do you need to estimate these total probabilities? Okay, so that's the question. Are we okay so far? Yes.
So right now, T, as opposed to the previous formulation, original formulation, now random.
Correct.
T is random.
Correct. Correct. I agree. I agree. I agree. Correct. Completely true.
Actually, I'm a little bit lost at this point.
Oh, okay. No, I'm so sorry.
Yeah.
Sorry.
These are the sums of the probabilities of those things that you observe, right? And
Correct.
In general, they're not uniform, but in your formulation, you've estimated this.
Right. Yes.
I think you might just
Sure. Okay. So I apologize. You have a distribution P. This distribution can be anything. Can be uniform, can be non-uniform, and so on. If you try to estimate, so let's say it's a distribution over all the English words. So it's a distribution over 500,000 words. There are different probabilities and so on. If you try to say, okay, tell me, you want to estimate this distribution to L1 distance, let's say 10%, we know before you need at least something that's proportional to 500,000. Now, so what we say is this. Suppose now you're trying to estimate not this deterministic vector, P1 probability of the word the, probability of the word house, and so on. We're going to say, take a sample. So, and then once you observe the sample, let's call T1 the total probability of things that appeared once, T2 the total probability of things that appeared twice. So you take a sample, you take a document of size 1,000, you'll see certain words. You'll see the word house, you'll see the word cat, and so on. Let's say house and cat appeared once. What I'll ask you is, what is the sum of the probability of house and cat? And what is the sum of all the probabilities of things that appear twice, and so on? So that's going to be the vector T. And we're trying to estimate this vector of probabilities.
Anything about what value to assign to T? Like, what are you going to assign to P1 if?
So, okay, so we'll see an example of something that you can do. So T1 is the total probability that you think all the things that appeared once have. Okay, that's going to be T1. We'll see an example of what to do. A little more tricky is what probability you assign to things that you have not seen. It's a little more tricky. Both of them are actually difficult. But T1, at least we'll see like a natural estimate right now. T0, it's not even clear what the natural estimate is.
The other thing is that if you have a very small sample, right, then to some degree you have few samples, but on the other hand, it's easy to estimate because you actually want to estimate something only on these small types.
I agree.
Whereas if you take a large sample, you have much data, but you also ask for more, right?
Yes.
So a priori, it's not even clear that it might be easiest to, with a single sample. I mean, a priori, if you don't do calculation, but strong magnetic should be the easiest if you have a single sample. Right?
Yeah. Well, so yes and no. Yes, I agree with you. What you said is right on. So what Professor Urbanke is saying is that what saves us is the fact that if I looked at sample of size n or something, then I only need to estimate at most n things. I don't need to estimate 500,000 things. Okay. So that is correct, and this is why this is even true. Otherwise, I'd be like trying to cheat you if I look at a sample of size 1,000 and I try to estimate 5 million parameters. So here, if my sample is of size 1,000, I'm only estimating 1,000 parameters, not estimating 500,000 parameters. So that's why this is possible. Okay. However, what is not exactly correct is if I saw something of size 1 I cannot estimate the probability because imagine that a uniform, I don't know, but I take one sample, I see one value. That distribution it could be that this thing is probability 1. It could be that this comes from a uniform distribution of size of 1 billion, so I cannot estimate. So that means, so as it turns out, you can show that as the sample size increases, you can do better and better. That's the point, and you can do it uniformly, but size that does not matter. Okay.
So this formulation wouldn't be useful. You can use the estimator.
Right. I think. Yeah. So I was going to say next slide, but I've learned from a few slides ago. So it's a next slide. Maybe I'm wrong, but next slide will come back to exactly this question.
Okay. I'm a little bit confused about the motivation from the natural estimator to this formulation. So you're saying that that is the basis or the reasoning or the.
So I think we need to go back to the title of the talk. Title of this talk is the art of the doable. You cannot estimate the distribution. In reality, like a lot of information theory people often say, okay, you have distribution of a fixed size binary, let the alphabet size go to infinity. You could say the same thing here. You have distribution, let the number of, as you know, because you're working on this, the number of patients you get is not infinite. You get only a fixed number. You get like 1,000 patients. You need to do something with it. Okay. So if you want to estimate distribution over everything, that's impossible. But the only thing, so our line of thought is this: the only thing you can do is you have to give things that appear the same number of times. You have to give them the same probability. If two things appear twice, two things appear 4 times, you have to give them the same probability. Given that you have to give things that appear the same probability, the same number of times, you have to give the same probability. Equivalent. Look at the sum. So instead of looking at p, you look at 2p because you're given them the same probability. So just look at the sum and evaluate that quantity. That gives you a way to evaluate how close you are to the distribution. And it's based on the assumption that if things appear the same number of times, they have to have the same probability. Okay? And now we can estimate how close are you to this. So that's one reason. That's the motivation. Of course, you ask how is it useful. How it is useful, we'll see later on. Okay? So this motivation is this, that you have to do it. Usefulness, we'll see later on, as I said, next slide. Okay? Thanks. I'm glad to see that in spite of the level of light, people are still awake a little bit. Should we take a short break or continue to, like, we can take?
It's up to you. The food will be available in half an hour.
Okay. So it's up to whatever people want. Okay, so yeah, 2 people break. Yeah, get the lights up. How do I change? How do I turn them off? The light off. So if anyone has any other questions, I think I need the light too. Yes. Yeah. Anyone has a question? Yeah.
Yeah, those 700, like, is every click a new? It is.
It's 47. So I think, David, that I'm going to talk only about the first half. That's okay.
That's what happened to me.
Yeah.
You remember my first slide.
Right. Okay.
I want to get my students to see how
It's kind of question. The t depends on the sequence of.
Absolutely.
So in the when measure the distance, do you minimize over all the t or maximize over all the other t?
So we're looking at
all the sequence. Do you need to maximize over all the possible sequences?
No, we look at the probability that you're wrong. So it's
Or you
there's a
know
probability.
of the sequence, then you take
Because you have a distribution, you don't want the distribution. The distribution will have determined probability on this.
So the L1 distance you actually use.
So remember, we want to be close to the L1 distance to be, let's say, 1%, with probability bigger than 99%. Is it okay? Remind me of your name. Remind me of your name.
Something I didn't understand is regarding estimation. Because T is a plane based on the data you observe.
Correct.
So what do you mean by estimating that? Because you already have them, right?
But I don't know what T is. I don't know the distribution. So an underlying distribution, I don't know what it is. And now I observed like some words. Okay.
So you're saying that this estimation E is estimation based on the actual distribution. But then
So both T determined by T is a random vector that's determined by the distribution and the random things that you have seen. And E is also determined by the random distribution, by the underlying distribution and the random sequence that you have seen.
then what is like E0, for example?
E0 is the probability that you'll give to things that you have not seen at all.
Oh, I see. I think you mentioned it in
No, maybe I did not. It's a good question. It's a good question. Maybe I'll clarify.
But E0 doesn't depend on the
Everything will depend on what you've said. Everything will depend on what you have seen.
not E. It depends on the actual probability, right?
Everything depends on the actual probabilities and the sequence that you have seen.
Not T. T depends only on the data you observe, right?
But also, let's say you've seen the word Javad and the word David, okay? So T1, let's say Javad appeared once, David appeared once. T1 will be the probability of Javad plus probability of David. That is determined by the underlying distribution.
I have a student exactly working on that problem, which is a large alphabet problem.
Okay, good. Okay.
Estimating that 4 to the L possible sequence.
Oh, I see. Okay, yeah.
So it's large.
Yeah. Very good. Okay.
So we're trying to look for a formulation
Yeah, okay.
that helps us to make it doable.
Okay. Okay, very good. Okay. Yeah. Okay. So, should we start? Sid, should we restart? No, oh no, I'm sorry. Is that?
Just overnight.
What was the question?
The question?
Yeah, that you just asked.
I just asked shall we? I want to. I thought that you may take the maximum over all the possible sequences. Can you say yes?
Perfect. Thanks. Thanks. Okay, so I'm sorry. Yeah, but maybe let's. Okay.
Let's click on top. Just touch here. You see normal projection cinematics of what
Okay, I understand. Okay, yeah. So let's just let them. What did?
This is normal projection that you said to this
Oh, I see.
lighting.
Okay. Is this okay, Rudy? Is this lighting okay or?
This may be better for Leslie.
Yeah. Okay. All right. So should we continue? So two questions that people asked during the break that may be helpful. You're not sure. One question was, are we trying to estimate it for every sequence? And the answer is no. Remember, we're trying to estimate things so that we're allowing ourselves error probability, which is 1%. So we're allowing ourselves 1%. So we want to come up with an estimator such that with probability 99%, guys, please. So someone is going to give us some delta ahead of time. They'll say, okay, estimate it to a distance of maybe 5%. That's your delta. And we're allowing ourselves 1% error. So we'll come up with something such that after you take that many samples, S samples, we guarantee that with probability 99%, what we'll observe, what our estimate will be right, will be within a distance of delta of 0.5%. Okay, so that's one thing. Okay, so there's some error probability, and the other thing was whether what do these T and E depend on. So as David was saying before, when you try to estimate the actual probabilities, then P, the original thing was deterministic. You don't know it, but there's some P there that you're trying to estimate, but it's deterministic. That's the distribution of English words. It's fixed. You don't know you're trying to estimate. That was fixed. Your estimate dependent on this, on the data that you observe. estimate was random that depended on P and on the data. In this case, both of them depend both on the P and on the data. So if you look at English words, every word has a certain probability. After you take 100 samples, there'll be things that appear 0 times. You're looking at the sum of all those probabilities that you don't know. Okay, so this sequence will depend on the distribution and on the data, and this sequence will continue like before to depend both on the sequence and the data. Yes.
What I don't know, it's like this 1% in a distance or 99%, right? Like, are you doing that for every symbol?
No.
Like every symbol is
You're trying to come up with an estimate E0 up to En. You'll come up after you observe this many samples. So the way the process works is this: someone tells you, I want to estimate L1 distance. They'll fix the distribution. They'll say L1 or they'll say KL divergence. So I want to estimate L1 distance of 5%. Okay. Then you'll tell them, okay, I need that many samples, whatever the number is going to be here. Like we're claiming that for this will be constant, but if not, whatever that number is. After we do it, someone gives you so many samples from any distribution, and you need to come up with an estimate that will be within L1 distance 5% with probability at least 99%. There's always some probability that you'll be wrong because maybe by chance you're always getting the same letter and again, you'll be wrong. Okay. But we want the probability 99%, you'll be correct. If 99 is, probably it's not too small, but if it is too small for you, then take the 1%, turn it into epsilon, you just multiply by log of 1 over epsilon. Log of 1 over epsilon is just a small constant. Okay? All right. Yes. All right. Okay, so the first thing I want to show you is that estimating these total probabilities is non-trivial. It's not that by making this modification now is very easy to do. I want to show that that's not the case. So let's look at a very natural estimator, which is the empirical frequency estimator, as we've seen before. So we'll let NT be the number of symbols that appear T times. Okay, so and then the empirical frequency estimator will assign the probability that we'll assign to the things that appear T time, F for frequency, is just going to be T over N is the probability that it will assign to every given element. And you have, right, that we showed before, that's the empirical frequency. If things appear 3 times, probability you give each element is 3 over N. But now we care about the total probability, so we need to multiply by NT. Okay, so that's the probability that the empirical frequency estimator assigns to things that appear T times. So for example, F1 is going to be the probability that it assigns to things that appear once. 1 over N is the probability it assigns to each one. N is the number of samples. 1 over N is the probability it assigns to things that every element that appeared once. And we need to multiply it by N1. F2 is 2 over N times N2 and so on. And what is F0? 0, because it's 0 over N times the number of things that appeared 0 times. And so it's always 0. Okay? So this is always 0. One thing to note is this, that whether you can multiply N0, if you know the alphabet ahead of time, then you can multiply, you know what N0 is, you know which elements did not appear, okay? And you multiply by N0. If you don't know the alphabet, then you don't know N0, but in this case it doesn't matter because it's 0 in any case, okay? So an example, suppose this is the alphabet size again, and this is your sequence. We've seen the sequence before. F1, 1 is everything that you have a sequence of length 4, everything appeared once, you give probability 1/4, but there are 2 things that appeared once, so multiply by 2 is 1/2. So the probability that you give to things that appeared once is 1/2. F2, every element that appeared twice, you give probability 2 over 4, but there's only one of them, namely D, so multiply by 1 is 1/2. And F0 is 0, and that's always the case, right? So F0 is always 0. Clear? So this is the empirical frequency estimator. And the question, of course, is, maybe this estimate already does well. Maybe because we simplify the problem so much that now it's easy to do. Right? So that's the question. Okay? So what I want to show you is no. Even under this simplification, when you look at total probabilities, the number of samples that you need is still linear in the alphabet size. So you didn't simplify it in that sense. So if you look at the empirical frequency estimator, this estimator, and the number of samples that you need to estimate within any constant number is linear. So I want to show you that if you try to estimate these total probabilities to 2%, then you need almost K, 98% K. Okay, and is what we're trying to show clear? Okay, and the proof again, or the example again, is simple. So take a uniform distribution over 1 up to k. Okay, so now I don't need to take a collection of distributions. I can fix one distribution y. Beforehand, I said, you know, you need to take a collection of distributions and then show that the estimator is bad for at least one of them. Here, I can just take a specific distribution. Why? Because I'm looking at a specific estimator. So I just show that this estimator for this distribution is bad. I don't need to get. Okay. All right. Okay. So we want to show that to get to estimate to within 2%, you need at least 98% K. So suppose that you took less than 98% K samples. Okay. Then what will happen is it's also clear here, right? I mean, then we'll observe at most 0.98 K symbols, and that tells us that. Yeah, that tells us that, yeah, there are 2%. So we took 98% samples. We see at most 98% of the symbols. So there are at least 2% of the symbols that you have not seen. But this is a uniform distribution of a k element. So what is T0? What is the total probability of things that you have not seen? Total probability of you have not seen is that each one is probability 1 over k because the uniform times 0.02 k. So it's at least 2%, right? Because you have not seen at least 2% of the symbols, the total probability, because it's uniform, is at least 2%. Okay. However, remember that F0 is always 0, right? So F0 always assigns 0 probability to things you have not seen. Okay. So just on the difference between F0 and T0 is 2%, right? And therefore, the L1 distance between the actual total probabilities and the empirical frequency is the summation of the differences. It's at least this difference on the first element. Okay, so therefore, if you take less than 90% 8K samples, empirical frequency will have an error of at least 2%. This estimate is correct, is biased, because T0, it always gives some positive, gives 0, whereas actually it has some positive probability, correct? Right. That's right. So I think maybe the next one says no. Okay, it doesn't. So that's correct. So you could pick any number and you'll get any. Yeah, that's correct. But what I want to show is that if remember, I picked 0.2 because remember that actually no, because I want to show that you need a linear sample. So you could have picked half and you'll get half. Just any number that you pick, you'll need a constant fraction. Right. Right. Okay. Any questions? Okay, so that shows you that the modification of looking at total probability doesn't at least trivialize the problem. All right. Okay, so this is we're good in Turing looked at the problem, and they were working on trying to break the Enigma code in World War II, and they're trying to estimate the probability that the YouTube commanders YouTube. Right. Right. The U-boats are going to choose certain passwords, and they came up with an estimator that actually is very close to the empirical frequency estimator. The probability that the good Turing estimator give things that appear t times is just the empirical frequency estimator of t+1. That's it. They're just shifting. That's it. Okay, so so the probability that they'll give to things that you've seen 0 times is going to be the total probability that the empirical frequency gives to things that you've seen once, and so that's the estimator. No. No, it's not. Correct. Correct. That's it's different because the Laplace estimator also will not work here. I didn't show, but that's a good thing to look at. Laplace estimator, what it does is you look at the things that appeared. Okay, Laplace estimator will look at things that appeared. Right. So Laplace estimator, you look at. If you want me to write, I'll write, but I'll say in words. And if you want me to be clear, I will. So what Laplace estimator does is you look at things that appear t times. You look at a specific element that appear t times, and then you add 1 to it, and then you normalize. Okay. So Laplace estimator. So Laplace. So let's say x appeared t times. So Laplace, so let's call it, so f of x is going to be proportional to t, right? Right. Take t and you normalize by n. In fact, it's equal to t over n. Correct? That's the empirical frequency for specific x. Okay. Laplace of x will be proportional to t plus 1. So if something appeared once, you pretended it appeared twice. If something appeared 3 times, you pretended it appeared 4 times. Proportional to t plus 1. So now it's going to be equal to t plus 1 divided by summation. I don't know how many elements, depending on how many, the denominator will depend on how many things you've seen. You need to normalize them so it's a distribution, okay? So that's the difference here. But now we're looking at, so this is for us, for probability of elements, right? That's what we talked about before. Now we're talking about combined or total probability. Okay, if you look at total probability, then empirical frequency f of t, so maybe I wrote it as f underscore t like this, ft is going to be equal to t over n times nt, correct? That's what we said. Laplace is going to be t plus 1 divided by some normalization, whatever, t plus 1 divided by summation of t plus 1. You see, like if there are only 2 elements, actually, so this is going to be, we can write, this is going to be n plus the size of the alphabet, plus k. Right, because each one you add 1, so it's n plus k. So this is going to be t plus 1 over n plus k times nt, okay? This is the Laplace estimator, okay? And good Turing, G of t is going to be proportion, so you need to modify, so now it's not going to be t plus 1, but it's not going to be n, what do I write, n plus 1, this n plus k. So it's going to be t plus 1, there'll be a different normalization factor, and then times n of t plus 1. Because g of t has to be f of t plus 1, which is f of t plus 1 is t plus 1, n of t plus 1, okay? And you need to normalize them, okay? And now, so the difference between them is that good Turing takes Laplace and then multiply it by nt plus 1 and divide by nt. So it takes the number of, it looks at how many things appeared one more than what you have seen, multiplies by that, and divide by how many things that appear the same number of time. Does that make sense? So the idea is, roughly speaking, that if you've seen something, if you're looking at trying to estimate the probability of something you've seen 5 times, many more things appeared 6 times, you want to increase the probability because I think it's more likely comes from a higher probability because some kind of distribution. Okay, so it's a little different. All right. Okay, so good Turing. So it's ft plus 1, which is so the probability of unseen mass. So empirical frequency gives 0, and good Turing will give f1, which is n1 over n. Okay, and it's unbiased. We'll show later. And it's a basic tool in language processing. Okay, and the question is, how many samples does good Turing need to estimate a distribution to within, to total probability to within delta? Okay.
I asked before, how do you do the edge effect of the maximum limit?
Okay.
Suppose maximum number occurs in the particular one is 10, nothing occurs 10, and you do good Turing for the 10, for 10 is f of 11, f of 11 is 0 because no empirical figures for 11, there will be 11 times.
Mm-hmm.
So that means you put 0 probability to any event that any of the things you have 10 times. That means you most likely occurring element has 0 probability. 0 definitely. They renormalize it somehow, right?
Okay, very good question. So what Chandra is asking is we're looking at ft, which is gt, which is ft plus 1. So what if trying to estimate the probability of things that appear 10 times, we're going to give it the empirical of things that appeared 11 times. But suppose nothing appeared 11 times, the empirical frequency will give that 0 probability. So the things that appeared 10 times, we're giving them 0 probability because nothing appeared 11 times. Okay, so the answer the answer consists of a couple of directions. Okay, first of all, if you're looking at things that appeared once, because remember we're looking at L1 distance. Okay, so if you look at things that appeared once or twice, your sample was, let's say, size 1,000, right? Our results are not going to work for n equal. They'll work, but they're not going to be that meaningful for n equal 1 sample or 2 samples. As the number of sample increases, they'll become more meaningful. So suppose that the block length is length 1,000, okay, and you look at things that appeared once or twice, okay, then most likely the probability is very small, because if the probability was half, then they'll appear 500 times, okay? So their probability is very small. So you're okay on things that appeared a few times. Number one, you're okay making a mistake. Number two, typically there'll be many of them. And so they'll be kind of like they'll even out, okay? So that's one part of the answer. If you're looking at things that appeared size, if you look at your sample size is 1,000, you're looking at things that appeared 500, okay? So now you're looking at things that have high probability, like probably about half, and you don't want to miss them because that will add a lot to your L1 distance or your KL divergence, right? And therefore, indeed, good Turing does not work well on this domain where you look at things that appear many times. It works well on things that appear a few times, or not things that appear many times. We'll see it in 1 or 2 slides, okay? And the third answer, the third part of the answer is what actually in reality what people do is they smooth these numbers. So if you look at how many things appear 10 times, 11 times, and so on, and if you see some kind of a big dip or something, you think by mistake, you typically smooth them. That's what people do in reality. So does that make sense? So three parts to the answer. If you're looking at things that appear a few times, then it's okay that you miss them, and that's why it works. If you look at things that appear many times, like n over 2, then you cannot miss them, and indeed good Turing does not work well in that domain, and we'll see that people do something about that. And then the third part of the answer is that in real life, people smooth these numbers a little bit. Okay. So performance of good Turing. So good Turing, the first analysis was in 2000, and what McAllister and Shapiro showed was that with high probability, namely 1 minus 1 over polynomial in n, probably close to 1. And then we're using O tilde to ignore logarithmic factors. So if I say O tilde of n, they may be n log n and something like that. So I'll just simplify. So with high probability, for every t is the number of times things appear, your error is proportional to t plus 1 over square root of n. So here you see the answer to your question. If you're looking at t which is less than square root of n, you're doing well. Okay, and if your t is very large, then indeed there's a problem, and then you'll want to do something else. Okay? So if t is less than square root of n, then this contribution is not going to be very large. Let's say it's n to the 0.4. Its contribution is not very large, and then you can allow yourself to miss a few things here and there. All right. Okay. So the good thing about this is that it holds for all distribution, all k. K does not enter this at all. There's no k in this. So this holds no matter what k is. And the other thing is good for small t. If t is less than square root of n, then significantly smaller, then it's good. The bad thing is that it's bad for t which is bigger than square root of n. Gives you no bound. Okay. And also remember we're looking at someone was asking about L infinity. So this is more in line of the L infinity, but if you want to use it for applications like machine learning applications, classification, and so on, you need stronger measures. So it doesn't imply that the L1 distance will go to 0, even without this issue. Okay. Okay. So then people looked at combination of good Turing and empirical. So what they said is that this is Durk and Mansour. They said if you're looking at things that appear more than n to the 0.4, then don't use good Turing because they'll run into your problem, right? There are things that will appear and then not appear and so on. They use empirical frequency, and if things appear less than n to the 0.4, use good Turing. And with that, they also considered L infinity, and but you can modify the results and to show that that for L1 distance, the number of samples you need is 1 over delta to the 6, no dependence. And for KL divergence, you need 1 over delta cube. There's always like a difference factor of 2 because the KL divergence is roughly the square of the L1 distance. So those are essentially very similar.
Optimized, or it's
yeah, it's optimized. You get some error for the first one, the second one, the optimizing. So the good news again is independent of k. So there's no k coming in, and therefore it's finite sample complexity because it doesn't matter what k is. You need a constant number. And the bad news is that even if you ignore constants, so on all these I'm hiding constants and so on, if you want to be within L1 distance of 10%, then 1 over delta to the 6 will give you 1 million. Okay? And 1 million is actually a large number because in reality, for example, if let's say you want to do text, so clearly if you need 1 million patients is a very large number. If you need 1 million DNA samples is a very large number. But even for text, you might say, oh, there's so many documents out there. But in reality, text is not IID. Text has some structure. So what you want to do is you want to say, like, say, within a context of the last 3 words, what is the distribution on the next one? Okay, so you need to find this context appearing 1 million times. That requires a lot of, because there are so many different contexts, you will require a lot of documents. Okay, so is that clear? Okay, right. So so what are the results that we can get? So existing estimator, as we saw L1, you need people show that you can get 1 over delta to the 6, and KL 1 over, or you can modify the results at least to show that L1 and KL 1 over delta cube, but these are only upper bounds. So a couple of questions. The first is, can you improve this combination of good Turing and empirical by using a different combination? So different combination might be changed n to the 0.4 to something else, or take some linear combination of the 2 estimators, something like that. Okay, and the answer is no. Any such combination will require at least 1 over delta to the 6 and 1 over delta cube. Okay, so any combination of good Turing and empirical will not do any better. And then the second question is, can you find a better estimator? And the answer is yes. You can find a new estimator that achieve 1 over delta to the 4 from 1 over delta to the 6, and here in 1 over delta square. Okay, and then the third question is this optimal? Can someone come up with better estimators? And the answer is no. Any estimate will require at least 1 over delta to the 4 and at least 1 over delta square.
Since all of these are independent of k, something feels strange. So, for example, suppose instead of optimizing over ID distribution, suppose it was over pairs of, let's say a Markov source or something like that. Again, you could try to mimic Markov sources by, pair, like one Markov sources by a pair of symbols. And in principle, you're saying that it doesn't require any more samples to.
Yes and no. Yeah, it's a very good question.
So the constant factors, is that where it comes in, or something?
No. So this is what it is. It's a constant. That is, someone could give you the constant. We didn't try to optimize the constant, but this is a constant, whatever it is. Such this is true. Yes, and it would be really nice to extend this to. Oh, I'm sorry. Okay, so if I'm trying to see if I completely understand his question. So his question is this: he says it's a little strange that it's a constant, and I agree. It's a little strange, but it's correct. And he says, so imagine this is for ID distribution. So he says, okay, then let's look at Markov distribution now. Markov of order 1. Since this is a constant, every Markov distribution is also you can view it as a collection of ID distribution, one for every context, correct? And therefore, it's a new constant. But that part is not true. Because what does the constant mean here? It means that if you want to learn to within, let's fix delta to delta to, let's say 1%, you need some constant number, because 1 over delta to whatever, 1 over delta to the 4, 1 over delta square. Okay, that's the number you need. But now if you have a Markov distribution over alphabet of size k, the number of context is going to be proportional to k, and you need to learn each one of those. So you need this constant times k. So for Markov, it's no longer going to be a constant. Is okay? Because that would have meant that for any distribution, essentially order 1, order 2, you understand his question? He was...
Basically, the problem is that you just make mistakes, right?
No,
So you just kind of mix it around.
in some sense, but just to be, for the specific version that he asked, there's a simpler answer, which is you need a constant number of samples for every constant and every context. But the number of context is k, proportional to k.
Context is the state.
Is the state, correct. So, right.
But that only comes in because you have to go back from your estimator to the real world. It doesn't come in on the level of that estimator. It comes in if you want to say what this estimator means going backwards, right? Because you might just observe a particular state, basically that's what David says, and then you go, you get a sample, but it's basically a sample in it.
It's a good attempt. It's a good attempt. I applaud you for this, but it won't work because so Rudy's question is this: that the quote-unquote trick we're doing here is we're only learning things. What helps us is we're only learning things that we have seen. So we have a sample of size 1,000. Then if we have a sample of size 1,000, we are not trying to learn a billion parameters. We're only trying to learn a number of parameters, which is at most 1,000. Still, I think it's still surprising that we can learn those. With just 1,000, we can learn many parameters. But it is just the number of parameters, it grows with the length. So what he's saying is now apply the same. I agree with. I was a little glib. The way I was explaining it. But he's saying you don't need to learn all the parameters. Said multiply by k. Right? But he's saying that's not true, and what he says is correct, because you don't need to learn all the parameters. You only need to do the same trick and only learn it for the distribution, for the sequences that you have seen. Okay? But still, it could be that after everything that you have seen, you've only seen one symbol, because still there could be if your sample of size n, there could be n contexts, right? N states that preceded it, and after each one you only have one sample. If you only have one sample, you cannot learn, because we need that many samples. So it's still the same issue. Because it could be that for every constant you will see a constant number of samples. Like let's.
The context, I don't see the context. I mean, there's no parameter in the context here, right?
This is for but this I know this is for ID distributions. What do you mean?
So that's the same issue as I mentioned. It's a mixing function. In ID, you mix immediately, right? You start from one state and you immediately go to any random other state.
I think mixing takes it one level up. I think you can stay below that. It's just the number of samples that you have. Imagine that you go from every state to every state, no problem. But the thing is that the number of states, the number of previous contexts that you may have seen may be proportional.
I mean, it depends on what, because in general you know the context, right? Because the way you then, it depends on how you even convert from into this.
Yeah, possibly. But you see that. That if you see, no matter how long the length is, n, the number of contexts could be n over 2. So that means that in every context you've only seen 2 samples. But in reality, you need that many samples to learn, and you don't have that. So you will not be able to learn. You see, right? Okay. Other questions? Okay, so let me just, there's maybe 1 or 2 more lines. So first, that the improvement is by a factor of delta or delta square. So if delta is, let's say, 0.1, it's a factor of 100. So it's somewhat significant. You reduce the number of samples by a factor of 100. And 2, it's optimal. So again, because we're using information theoretic arguments, you can actually show that this is optimal. This was missing before. Okay, any questions? Okay, no questions? Then let me see what the next. Yeah, okay. So maybe take a break because it's 10:30, and then we continue after the break. Yeah.